This lecture introduces the method of integrating factors, one of the methods that you can use to solve some linear first-order differential equations. All right, first we want to consider a linear first-order differential equations of the form, right? dy over dt plus pt, which is a function of t, times y equals to q of t, which is a function of t. Then first we want to to see if we can use other methods, the methods that we already know so far, which is method that you can use to solve separable equations to solve this dE. Well, let's play around with it. So I can say this is y prime plus p of t, right, times y equals to q of t. And I can try to move the y. Well, in separable equation, you need to move y prime and y to one side and functions of t to the other side. Well, I can try to move this to the other side, right, to see if we can do anything with it at this point here. And I kind of stuck here, right, because I want to move y to the other side, which I did, but then at the beginning, I cannot move the p of t to the other side, so on and so forth. So that means we cannot use separable. This is not one of the separable equations, so we cannot solve it by separating the function of t and function of y on both sides. So no, we cannot use separable equations to solve this dE. Then we should actually try to solve this equation. Okay, so let's look at this equation again. It's dy over dt plus p of ty equals to q of t. Okay. And we look at the left side of this equation here. You have something similar to the product of the derivative. So you have y prime here, and you have functions, and you have y, right? And remember, if you have a product, you have y prime, you have y, and you have a function, and this is multiplied to 1. So the products, if you think about product rule in derivative, it will be something like this, right? So you have, if you have, let's imagine you have mu times y, and this is two functions in terms of t, and if you find the derivative of mu times y, it will be mu prime times y plus mu times y prime. Okay, so we compare this and these expressions. So in these two expressions, we have y prime and y, and we have pt and 1, and we have mu, right? So then I want to see that if I want to force these expressions to be similar to these expressions, then what should I do? I need to have mu of t, right? A function mu multiplied by y prime and here. So I can do one thing is I can multiply the whole thing here to these expressions to get mu times y prime plus mu by p times y. And again, y and mu and p are functions in terms of t. Okay. Then at this point, I want to force. So because this is mu times y prime. So these things right here, I want to force this equals to mu times y prime. How can I do that? So once if I force these two equal to each other, and once I can find the function mu that satisfies this equation, then I can multiply mu to both sides of these equations, and then I can try to solve for this differential equation. All right. So the next question is, can I find mu so that mu will satisfy this equation? Well, let's rewrite it here. Mu times y prime, right? Plus mu times p times y equals to, the right side will be mu times y, the derivative of mu times y. So mu times y, and take the derivative of it. What is mu? So then if we rewrite this product, that will be mu py equals to mu prime y plus mu times y prime. Okay. And then we can see if we can cancel something out. Mu times y prime is gone, right? And then here we have y, and y is gone. So what left over is mu p equals to mu prime. At this point, we can use, since this is the differential equations of mu, right, in terms of mu and a function p of t, and then since you have a products here, then you can remind yourself, okay, this is a separable differential equation. If it's a separable differential equation is fits the form, then we can just move mu to one side and p to the other side to solve for mu. Again, the goal is to find this mu function. The next step is gonna be, I will move mu divided by mu equals to p, right? And at this point, I just integrate both sides. dt. Okay, and then I have natural log of mu equals to the integral of pt dt, then mu equals to e to the integral of pt dt. So I just found this function mu of t, right? You can say is all these functions here are the function in terms of t. All right, once I found mu, then I can multiply that functions into these equations right here, right? So I found mu, then I consider the equation. I go back to the original equation when you have y prime plus p of y equals to q. Then I multiply mu to both sides, and I know what is mu, right? I can find mu by taking e to the integral of p of t dt. Multiply mu to both sides, okay? And then remember, once I multiply mu to both sides, the left-hand side will be equals to this derivative of this product, mu times y. So this will be equals to mu times y. The derivative of mu times y equals to mu times q. Okay. And how can we solve for y? Again, solving for y is our goal. At this point, we just integrated both sides in terms of t. Okay, integrated the left side, you will have mu times y equals to mu times q dt. And then And once you integrate it, then you should have a constant. Well, then y now will be equals to c over, I divide both sides by mu, right? Plus 1 over mu times q of t dt. So this is the solutions for this differential equation that we're looking for. Again, we're trying to find the equation y, like the solution for this equation, and then using a trick of like using the product's rule of the derivative, I multiply a mu function to both sides of the equations, so then I can manipulate the derivative and in order to solve for y at the end here. So the integrating factor, so the factor that I use, which is mu here, I multiply mu to both sides, and mu at this point is called the integrating factor. Okay. And then look at the solutions of y. I have mu, which is the function that I found using the integral of p of t. Is involve a constant. When you're finding a general solutions, this is just a general solution for the differential equation, so you always have a constant here. It involves the integrating factor, it involves the q of t. And then you want to ask, if you have an IVP, right? If you're given a differential equations and then you given an initial value, then how can you find the particular solutions? So the way that we can find the particular solution using this general solutions is, as always, we want to find what is a value of c, okay? And then again, we want to find y, right? In terms, and for y, when we have a specific c using this initial value, and c is still unknown, and mu of t, again, mu of t, you plug t0 in here, right? Plus 1 over mu of t, you plug the t0 into the function mu, and you want to integrate mu of t times q of t dt. Okay, so if you can find one of the elementary function for this integral, then you found that functions, and then you plug t0 and y equals y0 here, so y0 to find for c. But when you cannot find an elementary function for this integral, then you have to integrate this integral from t0 up to t. Okay, this is like the initial point, and you integrate it from the initial point up to the function value at t. And because you having t on your bounds, then you have to change the variable inside your integral to a different variable. We call it as a, sometimes I just use s. It's a placeholder variable for t, because you're using t as your bound, so you cannot have t inside your integral. So you have to change it to a different variable, right? And sometimes you can use a, b, c, d, so on and so forth, but sometimes, most of the times, we use s for a placeholder variable here. All right, so this should be your particular solutions to the differential equation if you're using integrating factors as a method to solve that differential equation. Now we can, so to summarize all the steps using integrating factors to solve a linear first order differential equation, you can first find the function mu, right, equals to e raised to the integral of pt dt, and you substitute mu into this formula y, which is the solution for the differential equation here. When you have c as a constant, mu is a function that you just found here, and the integral mu t qt dt. You integrate it to find your general solutions, and if you have an initial value, then you plug t0 into other t, and if you using integrals, definite integrals, you want to integrate these functions from t0 up to t, and you want to replace the t, the variable t inside these integrals here using a different name, let's say s, right? All right, let's do an example. Well, you have differential equations and initial value, so this is an IVP, okay? Well, first, let's identify what is P of t. Keep in mind that you have the form, the equation form, which is Pty equals to Qt. And you want to identify, in this case, what is P of t, what is Q of t. So this is P of t, and this is Q of t. Okay, keep in mind. All right, so the first step, if you want to use integrating factor, the first step is step 1. You want to find mu of t, and mu of t equals to e raised to the integral of p of t dt. Okay. Well, now you can try to find this mu of t, and the p of t is e raised to 2 over x dx. Well, in this case, x is the independent variable. That means I need to use x instead of t. All right. So what is the integral of 2 over x dx? In calculus 2, we know that is natural log of 2 natural log of x. Okay. And in this step, you want to assume that the constant is 0 in this step. So then you can simplify this. It's going to be equals to just same as e to the natural log of x squared. So it's going to be just x squared. So mu of x equals to x squared. Then step 2, you want to find y, right? Y of x equals to c over mu of x. I just rewrite the equation now. The formula, this is mu of x, and then this is mu of x times q of x dx. Okay, q of x is e to the x, and mu of x is x squared. So we just plug it in. I can replace this equals to x squared. All right, now our goal is we want to find this integral. And in calculus 2, you can find this integral, you can integrate it by part. Okay. Well, let's remind us how to do this, how to find this integral integration by part here. Put in a small problem. Okay. So you want to see let u equals to x squared. So du equals to 2x dx. And v equals to dv equals to e to the x, then v equals to e to the x. Okay. Then this integration will be equals to uv, which is x squared e to the x minus v du, which is 2x e to the x dx. Okay. And then the next question is we need to find this integral right here. And this integral here, again, using integration by part, is let u equals to x, so then du equals to dx, dv equals to e to the x, and then v equals to e to the x. And then this will be equals to, again, I just carry this down, right? Minus 2, and this will be uv, which is x e to the x, minus v du, which is the integral of ax dx. So this will give us, the answer is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Okay. Well, you take this integral and replace it here to continue our problem. So it's going to be c over x squared plus, 1 over x squared multiplied to x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And again, in this case, since I already have c and c is already counted in this step, I can just ignore this c. All right. Now, well, I can do some simplifications, right? So you can do the next step is just 2x squared plus, this is going to be e to the x minus 2 e to the x over x plus 2 e to the x over x squared. This is y of x. So then this is the general solutions to this differential equation. Now I want to find, this is an IVP, so I need to find particular solutions. So I will just replace y of x equals to 2 and x equals to 1. C over 2, 1 is just C plus E over 2, 1 is just E, right? Minus 2E plus 2E. So then that means C equals to 2 minus E. All right. If C equals to 2 minus E, then my particular solution will be so this is the particular solutions. All right, so I just show you how to use integrating factors to solve a linear first order differential equation, and you can find general solutions and you can find particular solutions using one initial point. Okay, well, let's look at the direction field of this differential equation. So this is the direction field, the differential equations. And as you can see here that this curve here is a solution curve for this differential equation. All right, starting at the point x equals to 1 and y equals to 2. And I also sketch or trying to graph the solution curve that we found. This is the particular solutions here. And you can see that in this particular solution here does match the solution curve that we created from the vector field or from the direction field. This is how you can verify whether your answer is a correct answer or not using the direction field and using the solution curve. And also you can try to sketch or try to graph the particular solution that you found by solving it by hand. All right, the next part is we want to talk a little bit about the existence and uniqueness theorem for linear initial value problems. So for linear initial value problem, the existence and uniqueness theorem is straightforward. It says if you have a linear IVP, right? And you have, of course, you have a differential equation and you have an initial point. So then this IVP here will have a unique solution at any t0, at any initial value t0, where the homogeneous part P of t and the non-homogeneous part Q of t are continuous. And for every y0, that is the real value. It was saying as long as your starting point is a point that is a point on where the P of t and Q of t are continuous, then this IVP here will have a unique solution. Well, let's consider this differential equations. You have dy over dt equals to tangents of t, y plus secant square of t, right? And then your initial values is y0 equals 0. What does that mean? That means it's saying this is t0 is 0, and then y0 is 0. All right, so now in this equation, our tangent of t is P of t, and secant square of t is Q of t. Is that right? Oh, this is an equations in terms of like dy dt. And again, if you want to transform this equation to this form, then you can just take dy over dt minus tangents of t, y equals to secant square of t. Okay, and in this case again, so P of t here will be will include the negative. So to make sure that we are having we arrived at the correct form, we should move y of t to the other side to determine P of t more accurately. All right. So again, the function P of t is tangent of t, negative tangent of t, and the tangent of t functions is continuous everywhere. Also, the secant square of t, right? So the tangents of P of t here, tangents of t, negative tangent of t is continuous on the function tangent of t is continuous at 0. T equals to 0, right? Because t0 equal to 0. Also, the function secant square of t is also continuous at t equal to 0. So from this fact, we know that this IVP has a unique solutions. So once you find a solution for this IVP, is a unique solution. Okay. All right. If it has a unique solution, we should try to solve for it. You should try to find it. So using integrating factor, we can try to, so step 1, find mu of t. So mu of t equals to e to the negative tangents of t dt. Okay. So what is the integral of tangent of t? Or you can use, in this case, you can use, I can try to do it on the side here. So integral tangents of t dt. Okay. It's the same as sine of t dt, cosine of t dt. Okay. You use direction, you use substitutions to find this integral. So let u equals to cosine of t, then du equals to negative sine of t dt. Okay, so this integral will become negative 1 over u du. So then it will be just negative natural log of u, and u is cosine, so it's negative natural log of cosine of t. All right, so I replace this result here to continue my problem. So it's going to be e to the negative, say, negative, right, natural log of cosine of t. So it's just going to be cosine of t. It's absolute value of cosine of t. But in this case, we can just get rid of the absolute value because we want to have absolute value because we want to make sure that it's not negative when t equals to 0, is at least 0. So this is the first step. What about the second step? So the second step is you just need to, use the formula for y, right? So this y, so y of t equals to c over mu of t, which is cosine of t, plus 1 over cosine of t. Okay, integrate of cosine of t times secant square of t, right? Qt is secant square is 1 over cosine of t squared dt. Okay, well, the next question is, can you find this integral? So I will do it on the side. This integral right here is, if you, after simplifying this, you will have 1 over cosine of t dt. I don't know, you remember there's a trick when you learn, the trick that you learn in second calculus 2, that this integral here, you want to multiply. So this 1 over the cosine is a secant, right? Secant of t, and you want to multiply to secant of t plus tangents of t. Okay, and also divided by the same secant of t plus tangents of t, again dt. All right, and this point you can use substitution to find this integral. So let u equals to secant of t plus tangents of t, then du wanna be equals to secant square of t plus secant t times tangents of t dt. Okay, so you can see that if you multiply this, distribute secant of t into this part, you will have secant square plus secant times tangent of t, which is du. So this will be equals to just 1 over u du. Then it's just natural log of u, right? And u is secant t plus tangent t, so the answer is natural log of secant t plus tangents of t. All right, again, we can ignore the constant in this part because we already count the constants in the formula. Okay, so now we just keep continuing our solutions. It's gonna be 1 over c over cosine of t plus 1 over cosine of t times 2 natural log of secant t plus tangents of t. Okay, so this is our general solution. This is a plus. Now we have an initial value, which is 0, 0. So if you plug the initial value, y0 equals to 0, then we would have 0 on this side, right? Equal to c, cosine of 0 is 1, plus 1, right? And the secant of 0 is also 1, and tangent of 0 is 0. So it's natural log of 1. And well, natural log of 1 is 0. So what does it mean? That means c equals to 0. Okay. If c equals to 0, then the particular solution that we found is 1 over cosine of t times natural log. Here, I'm going to combine this two. So I would have natural log of secant t plus tangent t over cosine of t. So this is your particular solutions. And this is your general solutions. All right. So here you go, a method to solve some first linear differential equation and using integrating factors. This is called method of integrating factors.